picture this. You are sitting in like a sterile room. Fluorescent lights are just buzzing overhead, and you are staring blankly at a computer screen.
Sounds incredibly stressful already.
Oh, it is. Because you're taking the TEAS or the HESI, those high-stakes entrance exams you literally have to pass to get into nursing school.
Right.
And the clock in the corner is just aggressively ticking down. You're not allowed to use a calculator for this section. And right in front of you is this incredibly intimidating fraction, something like 72 over 108.
Oh, wow. Yeah.
Or maybe it's a really complex multi-step dosage calculation, and you are just stuck staring at these massive numbers. The anxiety spikes. I mean, how do you simplify that in seconds rather than minutes?
Yeah, that's where mathematical paralysis just sort of sets in. Your brain completely freezes.
Exactly.
Because you need to reduce that fraction to keep moving, but doing the long division by trial and error, that is going to eat up, well, basically all your remaining time.
It really is a high-stress scenario. You feel like you're trying to chop down a tree with a butter knife. But what if you could just look at those numbers, like literally just glance at their digits and instantly know their mathematical DNA?
Which sounds like magic, but it's not.
Right. And that is exactly the mission of this deep dive. Today, we are exploring the rules of divisibility. And just to be clear right up front, we are not talking about dry, trivial math facts you just memorized for a quiz.
No, definitely not.
These are highly practical arithmetic cheat codes. They let you know if one number divides evenly into another with zero remainder without ever actually doing the long division.
Yeah, and to put it in a slightly more, technical frame, these rules are essentially compressed proofs of modular arithmetic.
Okay, that sounds intense.
It sounds fancy, but they just exploit the hidden underlying patterns in our base 10 number system, our decimal system. They allow you to predict a number's mathematical family just by looking at its digits. It's actually quite profound when you peel back the layers.
Which is exactly what we're going to do. We're going to cover the core tricks you absolutely need to know to survive these timed exams.
Yep.
And we'll also look at the surprising history behind who actually invented them, plus the dangerously flawed mathematical systems those early pioneers relied on.
Oh, the flaws are fascinating.
Right. And we'll get into the great debates among math teachers today and exactly why mastering these cheat codes unlocks a whole new level of mental math for you.
I think the best place to start is with that transition from pure memorization to true understanding. Because surviving a timed exam by merely memorizing a list of rules, well, it's fragile.
Because panic makes you forget the list.
Exactly. Panic wipes the slate clean.
Oh.
But if you understand why the simplest rules work, you really don't have to memorize anything at all. The logic just does the work for you.
So for the simplest ones, I'm talking about the rules for 2, 5, and 10. I like to use what I call the bouncer analogy.
Okay, I love this analogy.
Yeah, so think of a number as a line of people trying to get into an exclusive club. And the club is divisible by 2 or divisible by 5.
Right.
Now, in our base 10 system, every place value from the tens place onward. So the tens, the hundreds, the thousands, the millions, they are already multiples of 10.
Because 10 times 10 is 100, 10 times 100 is 1,000?
Exactly. And because 10 is completely divisible by 2 and by 5, all those higher place values are VIPs. They are automatically on the guest list. They just walk right into the club.
So the hundreds place doesn't matter, the 10th place doesn't matter, they're already cleared.
Right. The only digit that is at risk of ruining the whole party is the ones digit, the very last number in line. So the ones digit acts as the bouncer. For the entire number to be divisible by 2, that bouncer just has to be an even number.
Makes perfect sense.
And for 5, the bouncer has to be a 0 or a 5. For 10, it has to be a 0. You literally ignore 99% of the number and just check with the bouncer at the end.
Which is a perfect illustration of how base 10 structure just does the heavy lifting for us. But that bouncer logic doesn't work for everything.
Right. It has limits.
Yeah. Let's look at the rule for 3 and 9. This is where you actually have to consider the whole number. So the rule for 9 is you just add up all the digits.
Okay.
If that sum is divisible by 9, the original number is 2. And the exact same process works for 3.
Okay, let's use 4,731 as a test subject.
Perfect. So we simply add the digits. 4 plus 7 plus 3 plus 1.
Which equals 15.
Right. 15.
Right.
Now we ask, is 15 divisible by 9?
No, definitely not.
It isn't.
Right.
So 4,731 is not divisible by 9, but is 15 divisible by 3?
Yes. 3 times 5 is 15.
Exactly. Therefore, 4,731 is absolutely divisible by 3. And if you checked it with long division, it's exactly 1,577.
See, here's where my curiosity always spikes. Why do 3 and 9 care about the whole entire line of digits when 2 and 5 only care about the bouncer at the very end? Like, what is mathematically different about 3 and 9?
It all comes back to a foundational fact of modular arithmetic, which, by the way, is just the formal math of remainders.
Okay.
So think about the number 10 in our base 10 system. If you divide 10 by 9, what happens? You get a remainder of 1.
Right. 9 goes into 10 once, with 1 left over.
Now look at 100. 100 divided by 9 is 11, with a remainder of 1. 1,000 divided by 9 leaves a remainder of 1.
Wait, really? Every single one?
Every single power of 10 leaves a remainder of exactly 1 when divided by 9. Because of this structural quirk, every place value effectively just leaves its digit behind as a remainder.
Oh, wow.
Yeah. So to find the total remainder for the whole massive number, you just sweep up all those leftover digits and add them together. That is why the digit sum works. It's incredibly elegant.
I honestly never thought about why adding the digits works. I just blindly trusted that it did. But we need to address a trap here, because there is a classic logic trap that really trips people up on exams.
Yes, the reverse logic trap.
Right. Students often assume that if a number is divisible by 3, it is automatically divisible by 9, because, 3 goes into 9.
It's such an easy assumption to make, but the reverse is absolutely not true. Just because a number passes the test for 3 does not mean it gets to pass the test for 9.
Yeah.
I mean, the number 15 is the perfect example. Like we just said, 15 is clearly divisible by 3. But it is definitely not divisible by 9. You simply cannot work backwards up the chain.
You have to be super precise with the direction of the rules. But once you wrap your head around that base 10 structure, you can start seeing how the rules for larger numbers scale up, like that they combine sort of like building blocks.
Exactly.
We talked about the bouncer rule for 2. Let's scale that up for 4 and 8.
Sure. So for 2, we looked at the last digit, right? Because 10 is divisible by 2, but 10 is not divisible by 4. So we have to ask, what is the first power of 10 that is divisible by 4?
Well, that would be 100. Because 4 times 25 is 100.
Right. Since the hundreds place is locked in as a multiple of 4, we only have to look at everything that comes after it. From the hundreds place onward, everything is guaranteed to be a multiple of 4.
Okay, I follow.
Therefore, the rule for 4 is just check the last 2 digits. If the number formed by the last 2 digits is divisible by 4, the whole thing is. And it scales again for 8.
Because 100 isn't divisible by 8.
Exactly. But 1,000 is. So for 8, you check the last 3 digits.
Let's run the number 3,816 through those checks.
Good number. First, we test for 4. Look at the last 2 digits, 16. Is 16 divisible by 4?
Yes.
So 3,816 is divisible by 4. Next, we test for 8. Look at the last 3 digits, 816. If we divide 816 by 8, we get 102, exactly.
Yeah.
So yes, 3,816 is also divisible by 8.
Wait, hold on. If I have a number and I test it, and I find out it is divisible by 2, and then I test it, and it's also divisible by 4, why do I even need a rule for 8? Can't I just say, hey, 2 times 4 is 8, so it must be divisible by 8?
Oh, no. You cannot multiply them together like that. Let's look at the number 12.
Okay.
12 is divisible by 2. It is also divisible by 4. But 12 is clearly not divisible by 8.
Ah, because they overlap. Like 2 is literally inside of 4.
Yes, precisely. When you test for 4, you are already implicitly testing for 2. They share common factors. To combine divisibility rules by multiplying them, the 2 numbers you are testing must be coprime.
Meaning they share no common factors other than 1.
Right. Coprime.
And that brings us perfectly to what I like to call the Frankenstein rules. The rules for composite numbers, which are honestly super relevant for the nursing entrance exam.
Oh, absolutely.
Take the number 6. There is no special, unique mathematical magic trick just for the number 6. It's a Frankenstein monster stitched together from other rules.
Because 6 is made of 2 times 3. And because 2 and 3 share no common factors, they're coprime, you can test them both. If a number passes the test for 2 and passes the test for 3, it definitively passes the test for 6.
So imagine you're back in that exam room, you're calculating a drug dose, and you end up with the fraction 144 over 6.
A very realistic scenario.
Right. Before you start doing messy long division to see if it reduces cleanly, just check the rules. 144 ends in an even number of 4, so it passes the 2 test.
Yep.
Then add the digits. 1 plus 4 plus 4 equals 9. 9 is divisible by 3. It passes the 3 test. Since it passes both, 144 is completely divisible by 6.
Yeah.
You never need to memorize a special rule for 6 or 12 or 15 ever again. You just test their coprime pieces.
It's incredibly empowering when that finally clicks. You're suddenly navigating these numbers with, like, X-ray vision.
It really is. And these rules are so logical, so perfectly built into the system, it makes you wonder who actually sat down and figured them all out.
Right.
It turns out these cheat codes were born out of absolute desperation in a world before calculators. But the early versions had some pretty fatal blind spots.
Yeah, there's no single inventor here. This is a story of global mathematical evolution. If we trace the origins back, we find ourselves in ancient India and the Islamic Golden Age.
Okay.
Mathematicians there developed a technique called casting out nines, which is fundamentally just the divisibility rule for 9.
Right.
But they used it as a fast way to check their arithmetic after doing large calculations.
And this made its way to Europe thanks to Leonardo of Pisa, who we know better as Fibonacci.
Right. In his famous 1202 book, Liber Abaci, Fibonacci was essentially a transmitter of knowledge. He brought Hindu-Arabic numerals and these arithmetic shortcuts to European merchants. You really have to put yourself in their shoes. These merchants were running complex ledgers entirely by hand. They desperately needed a fast way to audit their books to check their multiplication without redoing the entire math problem from scratch.
So they're relying on this casting out nines trick to ensure their entire financial livelihood is accurate. But there's a huge, devastating blind spot built into this, right?
Oh, a massive one.
Yeah.
Because casting out nines relies on the sum of the digits. Think about what happens if a tired scribe accidentally writes 39 instead of 93.
Oh, a classic transposition error.
Exactly. The sum of the digits is still 12. The rule won't catch the error.
It's a completely silent mistake.
Yes. Or if someone accidentally inserts an extra 0 or an extra 9 into the ledger, the sum modulo 9 doesn't change at all. The error remains completely invisible to the test.
So Renaissance bookkeepers were banking their fortunes on a system that had a mathematically guaranteed hole in it.
Yeah, pretty much.
That is the definition of false security. So if Fibonacci gave the merchants this somewhat flawed hand tool who actually built the whole factory.
For that, we move forward to circa 1654, to France, and Blaise Pascal.
Okay.
Pascal is famous for a lot of things. Pascal's triangle, his philosophical wager. But he also wrote a manuscript where he laid out the universal framework for divisibility.
So he didn't just invent a rule. He proved how to make a rule for literally any number.
Exactly. He computed the remainders of successive powers of 10, just like we talked about earlier with the nines leaving a remainder of 1. Pascal proved that you could use these sequences of remainders as weights to build a test for any divisor you wanted. He showed that the structure of base 10 mathematically demands that these rules exist.
But here is where we run into a major controversy. Because just because Pascal proved you can make a rule for any number doesn't mean you actually should.
No, it is not.
Which brings us to the great rule of 7 debate.
Ah, yes. The infamous rule for 7.
I have to laugh because it is so incredibly clunky. The rule for 7 goes like this. You take the last digit of the number, you double it, you subtract that from the remaining digits, and then you just repeat that process over and over until you get a number small enough that you recognize whether it's divisible by 7.
It is the definition of a brute force restatement. It completely lacks the elegance of the digit sum for 9 or the bouncer for 2.
Honestly, doing all that doubling and subtracting sounds like it takes longer than just doing the long division.
And many math educators argue exactly that. There is a real pedagogical divide here. Some curriculums insist on completeness, like teaching a rule for every digit 2 through 10.
Right.
But many TEAS and HESI prep guides explicitly tell students, skip the rule for 7. Just don't bother memorizing it. Under time pressure, performing that awkward doubling and subtracting process is often slower and far more prone to arithmetic errors than simply doing the standard division.
So the official advice for 7 is basically, just divide it, folks. Don't be a hero.
Pretty much. In a timed test, utility beats completeness every time.
Well, 7 might be a messy disappointment, but we can't let that ruin primes for us. Because other prime numbers have elegant, almost magical rules that test takers totally overlook. We need to explain the trick for 11, because it is wild.
The rule for 11 is one of my absolute favorites because it's just so striking. It relies on an alternating sum of the digits.
Oh, okay.
You go from right to left, and you alternately subtract, and add the digits. If the final result is divisible by 11, the original massive number is 2.
Let's walk through an example because applying this in real time is incredible. Let's use the number 918,082,
Yeah.
a massive 6-digit monster.
Perfect. So we start from the right with the ones digit.
Okay, that's a 2.
Right, and we alternately subtract and add as we move left. So 2 minus 8.
Which is -6.
How's a 0?
Still -6.
Minus 8.
Down to -14.
Plus 1.
-13.
And finally, minus 9.
Which brings us to -22.
Exactly. Now, is -22 divisible by 11?
Yes. 11 times -2 is -22.
There you go. Therefore, that massive 6-digit number, 918,082, is perfectly divisible by 11. It chops it down to size in seconds.
So I don't even need a calculator for a 6-digit number. I can just collapse it down to a -22 in my head. But why does the alternating addition and subtraction work? Why does 11 behave like this bouncing wave?
It goes right back to those remainders we talked about with 9, but in reverse. Think about how 10 relates to 11. 10 is 1 less than 11.
Okay.
So if you divide 10 by 11, you could say the remainder is 10, or you could think of it as falling short by 1, a remainder of -1. Now look at the next power, 100. 100 divided by 11 is 9, with a remainder of +1.
Oh, the remainders flip back and forth.
They alternate. The tens place is short by 1, the hundreds place is over by 1. The thousands place is short by 1, the 10,000s place is over by 1.
That is wild.
Because the powers of 10 alternate between being a +1 remainder and a -1 remainder relative to 11, you just apply that exact same alternating positive and negative pattern to the digits themselves.
That is brilliant. The math is literally just reflecting the rhythm of the number 11 dancing around the powers of 10. But what happens if you do that alternating sum and you end up with exactly 0?
Ah.
Let's say my math gives me a big fat 0. Does that mean the test failed?
This is a huge misconception, and it causes students to second-guess themselves right when they have the correct answer. 0 is divisible by every non-zero whole number.
Because 11 times 0 is 0.
Exactly. So if your alternating sum results in exactly 0, congratulations. The test didn't fail. It succeeded. The number is divisible by 11.
That is such a huge relief for anyone who hits a 0 on an exam and panics. But what happens when you're staring at a massive 6-digit monster like 918,082 and you don't even try the rule? I know my brain immediately panics and assumes a number that ugly can't possibly break down cleanly. It just feels like an ugly number.
That is the psychological trap of magnitude.
Yeah.
You look at a large, random-seeming number, and your brain assumes it must be built out of horrible, complex primes.
Exactly. I assume there's no way it breaks down cleanly by simple numbers like 2, 3, or 9.
But divisibility is a property of the digit pattern, not the magnitude of the number. It has nothing to do with how nice the number looks on the page.
Right.
Assuming otherwise causes test takers to skip over incredibly easy 5-second checks that would save them massive amounts of time. You have to trust the rules, not your aesthetic judgment of the number. Let the bouncer check the ID. Let the digit sum do the work.
We've covered a lot of ground today. From the panic of the TEAS exam, to Renaissance merchants, to Blaise Pascal and his remainders. But what does this actually mean for you, listening right now? The core value here is that these aren't just isolated party tricks you pull out for a standardized test.
No, they are the foundation of working with numbers. Divisibility rules are the front door to prime factorization. They are the tools you use to find the greatest common factor.
Right.
When you need to simplify fractions for a dosage calculation, you are essentially doing rapid-fire divisibility tests to strip away the shared factors. It's how you turn a massive, scary fraction into something easily digestible.
It's how you turn 72 over 108 into 2 over 3 before the clock runs out. You check the 9 rule, you check the 2 rule, and you aggressively carve the number down to its core.
And connecting this to an even bigger picture, beyond the exam room, this underlying math modular arithmetic is everywhere in our daily lives. It is the math you use to align shifting work schedules.
How so? Like figuring out when nurses on different rotations will work the same day.
Precisely. If one nurse works a 3-day shift cycle and another works a 7-day shift cycle, you use the concept of coprimes and least common multiples to figure out that their schedules will overlap every 21 days. The math of divisibility tells you how cycles lock together over time.
So it's scheduling math. But it goes way deeper than that, doesn't it? It goes straight into our digital lives.
Oh, absolutely. It scales all the way up to the backbone of modern computing. like the RSA encryption algorithm.
Wait, the protocol that is actively protecting our digital data?
Yes. Your bank accounts, your private messages right now, it all relies entirely on prime factorization, and therefore it relies on divisibility.
But how does that actually work? How do primes keep my passwords safe?
The security of the internet is based on a mathematical asymmetry. It is incredibly easy for a computer to take two massive prime numbers that are literally hundreds of digits long, and multiply them together to get a gigantic composite number. But it is computationally almost impossible to do the reverse. If you only have that gigantic composite number, figuring out which two primes it was made from takes an unfathomable amount of computing power and time.
It's like mixing two colors of paint together. It takes 2 seconds to mix them into a new color, but it's physically impossible to unmix them back into the original colors.
That's a fantastic way to look at it. Your public key is that massive mixed-together number. Anyone can see it. But your private key, the thing that unlocks your data, are those two original prime numbers.
Wow.
Hackers are essentially trying to run massive divisibility rules to find those primes. But because the numbers are so large, without knowing the cheat codes, they are stuck doing the computational equivalent of long division for centuries. Divisibility and the extreme difficulty of finding factors is literally what keeps the internet secure.
That is just wild. The exact same mathematical principles I use to check a dosage calculation in a sterile exam room are the principles keeping my bank account secure online.
It's all connected by the fundamental structure of numbers.
Well, we'll leave you with this final thought to ponder. The next time you are staring at a seemingly random string of numbers, whether you're sitting in that testing center looking at a dosage chart, maybe reviewing a dense financial ledger, or heck, you're just stuck in traffic staring at the license plate in front of you, try to stop seeing it as just a single solid block of impenetrable value.
Right, look closer.
Instead, look at it as a secret code. It's a puzzle made up of prime building blocks, and with just a few quick glances, checking the bouncer, summing the digits, observing the alternating rhythm, it is a puzzle just waiting to be unlocked.